Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced this idea of the vector product in R3, and what I want to do in this video is I want to look at some properties of the vector product in R3, and from these properties I want to deduce an algebraic formula for the vector product between any two vectors in R3 that will be useful for actually producing some calculations. So moving over to the tablet. I said that we want to start off, well, the kind of main goal is we want to arrive at this formula that actually allows you to calculate the vector product between two vectors in R3. And in order to do that, what we need to do is we need to prove the distributive property of the vector product. So that's similar to the distributive property that we saw for the scalar product. So what do we mean by that? Well, we're going to write out our theorem here. Okay, hold on, it's just booting up. Okay, that should have come through. So we have our theorem. Our theorem goes something like the following. So we've got let U, V, and W be vectors in R3. Then we're going to have that U crossed with V plus W is equal to U crossed with V plus U crossed with W. That's what we want to try and prove. This is, in other words, is the distributive property for the cross product or vector product. Right? We're saying that it distributes across this addition between our vectors. So the proof of this is a little tricky, so let's go through it in detail. Okay, so how are we going to start off? Well, what we want to notice, well, there's a useful thing that we can use, which is we notice that U cross with V is the same as U cross with the orthogonal projection of V onto U. How do we see that? Well, let's draw our picture. So we can draw our picture that we had before, where I believe this was our vector V. We can think of, say, this red vector down here. This one can be U. And then we'll have, say, our blue vector would be this one up here, which is, in this situation, is our orthogonal projection of V onto U. And we can also write this angle in here as theta. Okay, great. So what we realize is, well, let's just look at the norm of U cross, well, we don't need to look at the norm. If we do U cross V, that is the same as what? That's going to give us U, the norm of U times the norm of V times by the sine of the angle between them, which in this case we've labelled as theta, times n, where n is this normal vector that we choose according to our orientation. Well, what we can realise here is this piece here is exactly just the orthogonal projection, right? Just using some simple trigonometry. Right, if we think of this as our hypotenuse, this is the opposite angle, and then we'll get that the product of the length of V with sine of theta is equal to the length of this thing. So in other words, this thing is equal to the norm of U times the norm of the orthogonal projection of V onto U times by n. And we spot straight away, right, that that is exactly U cross the orthogonal projection of V onto U. And that's true for any vectors U and V in R3. So that's going to be useful. Why is that going to be useful? Because when we start off, what we're not going to look at is we're not going to look at the vector U cross V plus W. We're in fact going to realize that that is equal to U cross the orthogonal projection of V plus W. So let's look at now the orthogonal projection of V plus W. So another calculation shows that. So we want to look at what? We've got the orthogonal projection of V plus W onto U. Well, by definition, that is equal to V plus W minus, we would have U dotted with V plus W over U dot U times U. And we can write that. Oh, I think things have disappeared again. Wait, just give me a minute. Okay, that should appear again now. Sorry about that. Okay, so we can rewrite this equation that we have here as equal to v minus u dot v over u dot u times u plus w minus u dot w over u dot u times u. So we realize that this whole thing here now is simply just the orthogonal projection of v onto u plus the orthogonal projection of w onto u. In other words, the orthogonal projection distributes over the addition. So the orthogonal projection of the sum is equal to the sum of the orthogonal projections. So that's kind of useful because let's piece all that together. So we started off with we wanted u crossed v plus w, and we now know that that is equal to u crossed the orthogonal projection of v plus w onto u, but we've just deduced that the orthogonal projection distributes over the addition, so that's the same as u crossed with the orthogonal projection of v onto u plus the orthogonal projection of w onto u. Now, what we're trying to figure out, we're trying to show that this distributes over this formula. So in other words, we want to show that this thing here is equal to u crossed with the first thing plus u crossed with the second thing. So if we can take this vector here, and we can take the other vector, namely u crossed with this plus u crossed with this, and we can show that those have the same point in the same direction, and they have the same length, then they must be the same vector, right? Because then this would deduce that this thing is equal to that other vector. So in order to do that, what we want to do is we want to take, for example, the dot product between this sum and our proposed vector. If we can show that that is 0, then they point in the same direction. And then we want to take the magnitude of that vector that we're proposing, in other words, this u cross projection of this plus u cross projection of this, and show that's the same as the magnitude of this, the norm of this, and then we will have finished. So in order to do that, in order to at least show the first part that the dot product case is true, we need to do another calculation in terms of kind of relating these cross products and projections that's going to be useful for our kind of proof. And in order to do that, let's draw a kind of picture so we can see how this is going to work. So I want to start off with, well, actually, let's also make a comment here. So we can notice that the orthogonal projection of v onto u, the orthogonal projection of w onto u, and the orthogonal projection of v plus w onto u all lie in the same plane. I say this because this will allow us to draw a nice picture, because if they all lie in the same plane, we can think of that plane as the surface of my tablet, and therefore I can draw this. Why do they all lie in the same plane? Well, they all lie in the same plane because they're all orthogonal to u, right? By definition, this orthogonal projection, the projection points in the direction of u, so the orthogonal projection must be orthogonal to u. So we can think of u here, say, as either pointing out of the surface of my tablet or into the surface of my tablet, and all of these lie in the plane, which is the surface of my tablet. Okay, and we also notice that by definition, if we see here that this orthogonal projection, because it's orthogonal to u, the angle between u and this vector, or this vector and this vector, is always pi over 2, which is going to be useful because if we ever take norms of it and we do the cross product or the vector product, it's the sine of the angle between them, and that we have sine of pi over 2, which is 1. So we would only have the relation with just norms. There's no sine piece involved there. So kind of given that, I can now draw a picture. So let's draw kind of my first vector here. let's think of this vector here as the orthogonal projection of v onto u. And I can take the other vector, this one here, which I'll write as a red vector, is in the same plane, so we can write it like so. We can draw it like this. So this is the orthogonal projection of w onto u. And in my calculation here, I also want to look at the cross product, what is the vector product of u with the orthogonal projection of v onto u. Well, we can draw that, so let's maybe draw that in this green vector here. If we're thinking of u either going in or out of the page, it must follow, by the definition of the cross product, it must be perpendicular to it. So we've got this green arrow here. And this thing here is now what? This is u crossed with the orthogonal projection of v onto u. Okay, and because we can move these vectors around freely, we can shift, kind of parallel transport this red vector to the tip of this yellow vector here. So we can write the red vector, I'll try it to draw it as best as I can. This here now, this red vector is the same as this one here. And we can write the angle between this green vector and the red vector. We'll call this thing here theta. Okay, and on top of that, we can also do the cross product between this vector and u, which we see is going to be this vector here. So it's going to be this blue vector that I'm drawing here. And this here now is u crossed with the orthogonal projection of w onto u. Right, again, this follows because this thing must be perpendicular to u, orthogonal to u, so therefore it must lie on this plane because u is outside of the pointing either into the page or out of the page, and it must also be perpendicular to this red vector. So this thing here is at 90 degrees. So maybe I can put this in at 90 degrees. And okay, and we can also maybe extend this out a little further. We see here that this angle here is going to be the same as the angle if we extend this thing out. It's going to be the same as this angle, and because this is at 90 degrees, this thing here must be pi over 2 minus theta. So that's the same as this one, which is pi over 2 minus theta. So maybe let's extend this out a little more. And we see that this here is pi over 2 minus theta because this here is at right angles. Okay, so we've got our nice picture. Why is that going to be useful? So let's look now at, we have in my calculation in the notes, so we have the orthogonal projection of w onto u. And we want to take the scalar product of that with u crossed with the orthogonal projection of v onto u. Okay, so how would we write that? Well, let's just use our formula for the scalar product. So for the scalar product, we're going to have that's going to give us the norm of the orthogonal projection of w onto u times by the norm of this whole cross product thing of the projection of v onto u times by the cosine of the angle between them, which we've written here as theta, right? In our picture above, we have that the angle between this vector here and this vector here is exactly this angle here, right? The angle between this red and green vector is this theta. So that's why we've written it as theta here. But we can simplify this a little further because we realize that this thing here can be expanded to write it as the norm of the orthogonal projection of w onto u times the norm of u times the norm of the orthogonal projection of v onto u times by cosine of theta. And you might say, well, where's the sine theta piece? Well, what's the angle between these two things? The angle between these two things is pi over 2 because this thing here by definition is orthogonal to u, and therefore sine of pi over 2 is 1, so we don't get the sine piece, we just get the two norms. Okay, so that's pretty neat. And now what we're going to do is we're going to use a neat trick here. We're going to write this now as minus the orthogonal projection of u of W onto U times by the norm of U times by the norm of the orthogonal projection of V onto U times by the cosine of pi minus theta. Right? And you can realize that if you expand this using the double angle formula, exactly what you're going to get is you're going to get exactly the previous formula, but up to a minus sign, which is why this minus sign has arisen here. Why is that useful now? Well, let's look at our picture up here. We realize that this angle, pi minus theta, is exactly the angle that we have between this yellow vector here and this blue vector, right? Because we have pi here, pi over 2 here, plus this vector, which is pi over 2 minus theta. In other words, this whole angle here is pi minus theta. So we see that the angle between the yellow vector and the blue vector is exactly this pi minus theta. So we can write this now as minus, exactly as I wrote in the notes, the orthogonal projection of V onto U dotted with U crossed with the orthogonal projection of W onto U. So our overall formula now is that we have that this orthogonal projection here dotted with this thing is equal to kind of minus the orthogonal projection of this dotted with this thing. Okay, so that's a neat formula that we're going to use in just a minute to prove what we wanted to prove. So what do we want to show? We wanted to show that our proposed vector, namely u crossed with this thing plus u crossed with this thing, points in the same direction as this whole thing here. So in order to do that, all we need to do is we need to show that if we take the dot product of this thing with our kind of proposed vector, if that thing is 0, then we must conclude that they point in the same direction. So that's our calculation that we're going to do now. So now we have the dot product. We want to do the orthogonal projection of, I'll write it as V onto U, plus the orthogonal projection of W onto U. And I want to dot that with our kind of proposed thing that we think it's equal to before was U cross the projection of V onto U plus U cross the orthogonal projection of W onto U. Okay, so we can expand this using our distributive property for the dot product. So this gives us the orthogonal projection of V onto U dotted with, we have U crossed with the orthogonal projection of V onto U plus the orthogonal projection of V onto U dotted with U cross the orthogonal projection of W onto U plus the orthogonal projection of W onto U dotted with U cross orthogonal projection of V onto U plus the orthogonal projection of U or W onto U dotted with U crossed with the orthogonal projection of W onto U. Okay, now we immediately spot that this thing here must be 0 because by definition in here we have a vector that is going to be orthogonal to the orthogonal projection of V onto U, and if we've got a vector that's orthogonal to that vector, then it must be the dot product is 0, and by a similar argument this one must also equal 0 because the vector that we get here must be orthogonal to this one, and if it's orthogonal to this one then the overall dot product is 0. So what we're left off with is those two remaining vectors, namely the orthogonal projection of V onto U dotted with U cross the orthogonal projection of W onto U plus the orthogonal projection of W onto U dotted with U cross the orthogonal projection of V onto U. But this is exactly what we've just proven a minute ago, that these things are the negative of each other, right? So if we go up here, see that this orthogonal projection of W dotted with this thing, which is exactly what we have here, is equal to minus this thing, right? With this thing here, which is exactly this expression, but with a negative sign. So the overall thing, when we add them together, is equal to 0, which is exactly what we wanted to show. So in other words, the vector u crossed with the orthogonal projection of v onto u plus the orthogonal projection of w onto u, and the vector u crossed the orthogonal projection of v onto u plus u crossed the orthogonal projection of w onto u point in the same direction. And I guess you could say this is dependent on the chosen orientation. So which direction it points depends on the orientation that you chose. If it was a left-handed orientation or right-handed orientation, regardless, this formula still holds. So all we need to show now is that indeed the length of this vector is the same as the length of this vector. So we need to just find the norm of this kind of long thing. So we would do the norm. So then we have then the norm of u cross the orthogonal projection of v onto u plus u cross the orthogonal projection of w onto u. Let's take the norm of this thing squared because it's a little thing easier to work with. What is that equal to? That's equal to the thing dotted with itself. So in other words, we get u cross the orthogonal projection of v onto u plus u cross the orthogonal projection of w onto u dotted with u cross the orthogonal projection of v onto u plus u cross the orthogonal projection of w onto u. Expanding, this gives us what? This gives us the norm of u cross the orthogonal projection of v onto u all squared plus the norm of u cross the orthogonal projection of w all squared. And then we're going to get plus, so let's make sure we got this right, plus 2 times by the dot product between the mixed terms, right? So we get this factor of 2 because the scalar product commutes. So in other words, we've got here u cross the orthogonal projection of v onto u dotted with u cross the orthogonal projection of w onto u. Okay, so we can expand these now using our kind of usual formulas. Again, we know that the sine of the angle between these things is pi over 2. So that makes that a little bit easier. So this is just simply going to be the norm of u squared times by the norm of the orthogonal projection of v onto u all squared. Similarly, we get a term like that here, the norm of u squared times by the norm of the orthogonal projection of w onto u all squared. And for this expression now, what we're going to get plus 2 times by the norm of u all squared times by the norm of the orthogonal projection of v onto u all squared. Oh, no, sorry, not squared. Get rid of that squared there. Times by the norm of the orthogonal projection of w onto u times by the cosine of the angle between these vectors. And we can figure out what the cosine of the angle between these two vectors are now. So we look up here, back at our picture. So we're looking between this u cross vector and u cross vector here. So going back up to our picture, in other words, we're looking at the angle between the blue vector and the green vector here. So if we kind of map that along, we realize that that is going to be the same. So the angle between this blue vector and this green vector, which is kind of going to be like this, and this one we know here is at 90 degrees. So this angle here is going to be the same as the angle between these two vectors. Oh, tablet's gone again. Sorry about this. Okay, and that should be working just again now. Okay, so from that argument, we can describe that thing here now as, we said, as pi. Well, we can just write that angle here as theta. We'll call it theta 1, which is the one that we deduced above. And from this, it follows then that what do we get? We're going to get that factoring out the norm of u, that's the norm of u squared all times by the norm of the orthogonal projection of v onto u all squared plus, we can factor out this as 2 times by, this is now the orthogonal projection of v onto u dotted with the orthogonal projection of w onto u plus the norm of the orthogonal projection of w onto u all squared. This is a rather tedious calculation, as you can see. So let me just go through that quickly because of the issues of the tablet. Why do we see that this is the dot product? Well, we saw here that the angle between our vectors, what do we have here now? We had the angle between these two vectors here. In other words, the angle between our blue vector here and our green vector is the same as the angle between these two here. So this is what I just called theta 1 just a minute ago. Okay. And from this, we can write our final line down now. That is the same as the norm of u all squared times, that is the norm of the orthogonal projection of v onto u plus the orthogonal projection of w onto u all squared. In other words, we realize that this whole thing here, which we've said is equal to this thing here, is clearly equal to the norm of this thing, right? Because if I take the norm of this thing up here, that's just the norm of u times the norm of this whole thing, because this thing must be orthogonal, and that's exactly what we've got here, but just with squares, because we did the whole expression, we've got the norm of u, so the norm of u squared. So in other words, what we figured out? We figured out that this vector, so hence, we have that this vector u cross the orthogonal projection of v onto u and the orthogonal projection of w onto u points in the same direction as u cross the orthogonal projection of v onto u plus u cross the orthogonal projection of w onto u, and they have the same length. Thus, our overall result is proven. In other words, u cross v plus w was the same as we said u cross the orthogonal projections, and we've deduced that the orthogonal projections are the same, so that is the same as u cross v plus u cross w. Okay, so we've moved through, we've written this as equal to u cross the orthogonal projection of this thing. We deduced that the orthogonal projections was the same as this thing here with the orthogonal projections, and therefore these two things must be equal. So that was a rather long proof, but that's kind of as proving the distributivity of the vector product. Now, using that, we can finally arrive at the useful result, which is our theorem for how do we calculate the cross product. So given the length of this video is already running quite long, and that calculation was rather tedious, I'll just state this and you can read the proof in the notes. It's just a simple application of the distributive rule. So if we let u equal u1, u2, and u3, and v equal v1, v2, and v3, be vectors in R3, then the vector product of u and v, and we should say, assuming right-handed orientation, there's a similar one for a left-handed orientation, is given by the following formula. So we have that u cross v is equal to u2 v3 minus u3 v2 times I minus u1 v3 minus u3 v1 times j plus u1 v2 minus u2 v1 times k. And the proof of that, as I said, is in the notes, and it simply just applies the distributive rules. So I'll just say proof, see notes. So read those in detail yourself. If you have any questions, come and see me in the office hours or contact me via email. So we've constructed all that, we've got our theorem. Now let's actually see if we can calculate an actual vector product between two vectors. So we'll go to our example. And we want to say, in this particular example, we let u equal 2, 1, 0 and v equal 1, 2, 1. So these are vectors in R3, we don't say that. Then the vector product of u and v is given by, so we have u cross v. We can write using our formula, so we write it as here as 2, 1, 0 crossed with 1, 2, 1. And using our formula above, we can simply write that, and writing it here in this row notation. So I've expanded these vectors of I, j, and k that were introduced as basis vectors in an earlier video. This can be just written as 1 times 1 minus 0 times 2. So this is just substituting in those values into this, substituting these values into that formula. That's minus 2 times 1 minus 0 times 1. This overall minus sign in front, don't forget that. Got 2 times 2 minus 1 times 1. Close our bracket. And we simplify all those down, you do the expression and you get 1 minus 2, 3. So using that formula above, we can deduce what the vector product is of these two vectors in R3 is, assuming a right-handed orientation, because that's the formula above is assuming a right-handed orientation, and that is going to equal this thing here. Okay, and then it follows from the kind of previous thing that we said that if we take the norm of this quantity, that the norm of this quantity corresponds to the area of a parallelogram spanned by the vectors u and v. So it follows that the area of a parallelogram spanned by u and v is given by the norm of this. So we take the norm of u cross v, which is the square root of 1 plus 4 plus 9. In other words, it is root 14. So that's kind of tying together some of the previous bits to this part here. So what we concluded in this video, we've deduced the distributive property of the vector product. That was our kind of long proof. From the distributive property of the vector product, we were able to derive an algebraic formula for the vector product. So we can now explicitly find the vector product between two vectors. And then we can also tie that in, because once we found the vector product, we can then write down what the area of the parallelogram is of parallelogram spanned by those two vectors by just taking the norm of that product. So that was quite a long video. That's where we're going to finish off now. And in the next video, we're going to talk about something called the scalar and vector triple product. So definitely in this video to read over the notes in detail, especially the proof of the algebraic formula for the cross product, and attempt any problems in the module handbook pertaining to the stuff that we talked about in this video. So thanks very much for watching, and see you in the next video.